Hello, welcome to the presentation of the paper titled Self-Supervised Classification for Detecting Anomalous Sounds. This research has been conducted at Amazon Web Services by Ritwik, Giri, Srikanth, Fangzhou Cheng, myself, Karim, Umut, and Arvindh Krishnaswamy. Let me please kick off the talk by giving an outline of the presentation. I will start by a problem definition and introduction, will introduce then our approach, present the results on the chosen dataset, and finally, we'll conclude the talk with a summary. The task we are solving in this paper is the following. Given a training set with audio recordings labeled as normal sounds, our goal is to flag sounds that are significantly dissimilar to these normal sounds. The dataset we are using is the recently released 2020 DCASE Challenge Task 2 dataset, which combines two recent audio datasets recorded from machines, namely Toy Atmos and Mimi datasets. The challenge task is unsupervised anomalous machine sounds detection. Anomaly detection can be solved in either supervised or unsupervised setting. The supervised setting requires a prior knowledge about the anomalous behavior, which might be challenging in a real-life scenario. Models to solve unsupervised anomaly detection belong typically to the family of descriptive models, such as density estimators, or generative models, such as autoencoder-based approaches, or a combination hereof, such as normalizing flow-based models. Looking at the problem of anomaly detection, it is more appropriately described as discriminating task. In this research, we would like to harness the power of discriminative models in solving the problem at hand. The idea we are following is to apply the concept of self-supervision to define classification tasks, hoping along the way to learn features which are discriminative to anomalous versus normal data samples. The classification tasks we are going to develop are based on the metadata accompanying the training data. In this case, the machine IDs accompanying the audio files in the dataset. What are the auxiliary tasks we are looking at? We experimented with 3 tasks. The first one is to identify the machine ID of an audio sample. It is basically a machine ID classification. For each machine type, we train a network to identify the machine ID that a recording belongs to. For example, for machine type toy car, the DCASE challenge dataset consists of 7 machine IDs. We train a network to identify the ID that a training sample belongs to. We define then an inliner score, which is the softmax classification score of a test sample measured at the output corresponding to its true machine ID. An outlier score is its negative value. The second and third auxiliary tasks involve augmentation steps. Please note, a successful technique for augmentation in an anomaly detection setting is different from a classical classification task data augmentation technique, in the sense that we do not want to make the classifier less sensitive to the variation in the input, but rather more sensitive. The auxiliary tasks involving augmentation are the following. We synthetically combine samples and try to identify the mixing ratio. Basically, data from different machine IDs are combined in pairs using randomized linear combination, and the network is trained to learn to identify the mixing proportions. For example, for an input sample that is a mixture of 0.4 x1 plus 0.6 x2, where x1 and x2 are samples from IDs 1 and 2, the network is trained to output 0.4, 0.6, 0, 0 for all other IDs. Kullback-Leibler divergence is used as the loss for this task. Linear combinations both before and after taking the log on MEL spectrograms have been considered. The last auxiliary task is pretty much the same as the first classification task, whereby we, however, introduce new classes, in this context, machine IDs, by perturbing samples of the original datasets. We perturb samples from existing machine IDs to create new machine IDs using image warping applied on the spectrogram of the samples. Specifically, for each machine ID, we synthesize 2 perturbed machine IDs by warping along the frequency axis. Here is an example of the warping along the frequency axis. The architecture we have been using for classification are off-the-shelf architectures. We have used MobileNet version 2 and ResNet 50. Please note that we have initialized our networks randomly to comply with a challenge requirement. The input to our network is 10-second file split into frames of length 64 milliseconds with a hop length of 32 milliseconds between frames. 128 mil pins using 1024 FFT are used to featureize each frame. 64 featureized frames are stacked to form a 64 times 128 image. The successive 64 times 128 images have an overlap of 56 frames. As a loss function for our auxiliary tasks, we have used 3 variations. The first one is a softmax loss for the straightforward classification task, Kullback Leibler divergence to identify the mixing proportion in the linear combination task. And we have also experimented with a recently introduced additive angular margin loss arc phase to increase the discriminative power of the feature embedding learned by the models. So to highlight that we are getting discriminative power from the self-supervision task for the primary problem at hand, which is discriminating normal from anomalous samples, we show T-distributed stochastic neighbor embedding plots, short TSNE, of features extracted from our machine IDs from the toy car set, using the mobile net v2 architecture and no augmentation. For machine IDs 2, 3, and 4, the separation between the normal and anomalous test samples is evident. For ID 1, self-supervision doesn't seem to perform as well. The AUC and PAUC numbers, also shown in the same figure, reflect this. To obtain these plots, 5,000 normal points are sampled from the union of trained and tested set, and 5,000 anomalous points are sampled from the test set. For comparison purposes, we also present the TSNE plots of the 64 times 128 input log-MEL spectrograms on the left side. As we have seen, a single self-supervision strategy doesn't seem to work well all the times. In our experiments, we found out that best performance is obtained if we train different models and use finally an ensemble of these different models. The models we experimented with are MobileNet, ResNet 50, with different augmentation techniques and loss functions as shown earlier. We have also included in the ensemble a novel density estimation model called GroupMade, which is also presented at this workshop. The ensembling is performed by transforming the anomaly scores of each model into a standardized scale before combining them. The standardization transformation for any given model is applied in a per machine ID fashion by computing the mean and variance of its anomaly scores over the training data for that machine ID. The anomaly scores are then transformed to have zero mean and unit variance over the training data of that machine ID. Standardized anomaly scores across different models are then combined using mean or max ensembling. Here we show the receiver operating characteristics curves, area under curve AUC and partial area under curve PAUC obtained on the DCASE challenge dataset. The development subset of the dataset is used in the results shown. For different machine types, different combinations of the augmentation mentioned above are observed to give the best results. The with augmentation results shown in the second table are obtained using the augmentations indicated in the table at the top. The benefits of augmentations are evident for most different machine types. The networks are trained using the Adam optimizer. The auxiliary classification task is observed to quickly converge for certain machine types. The number of epochs is varied across machine types accordingly, as shown in the upper table, and to avoid overfitting for the ARC-based results shown in the second table, the number of epochs was fixed to 25 for all machine types to avoid overfitting. In our experiments, we observe that the self-supervised approach described above performs very well when ensembled with the other anomaly detection approaches. For instance, ensembling with GroupMade yields the best results in our experiments on all machine types. To conclude this talk, we have introduced a novel anomaly detection approach based on the concept of self-supervision and designed auxiliary tasks to extract highly discriminative features for anomaly detection. We have shown how to apply audio-inspired data augmentation techniques. And finally, it is worth mentioning that this presented approach is the approach which won the task 2 challenge. Thank you for your attention.